Hello and welcome to a new episode of Library of the Week. This is part of a series of articles I write on Medium about Python libraries, and I try to do them weekly. I make a video for each article, and you can find the link to the article in the description of the video. Today I'm going to be talking about two different libraries. They are called Pelote and Ipysigma. The reason why I talk about two libraries is because they are very much related. They both are used to work with networks, with graphs. Pelote is a toolbox that has a lot of different functions to analyze and to trim and to work in general with a lot of network X objects, so graph objects. And Ipysigma is a Jupyter widget that allows us to display graphs in an interactive way. Also, both these projects are by the same group of people. They have been developed by Media Lab, which is a research lab from Sciences Po Paris. So Sciences Po is a very famous French university. And yeah, this is an academic project. So let's see how to use Pelote and Ipysigma with some examples. I'm going to start with an easy example. The first thing that Pelote allows us to do is to transform pandas data frames into network X objects with ease. So let's imagine that I have a pandas data frame with some stations from the Madrid metro. So I have some stations from line 1 and some stations from line 2. The data frame needs to be in a way where one column has the node and another column has the node that the previous node is linked to. So we can make the edges, right? And so the first thing is to define the pandas data frame. So here I have it. So df Metro Madrid. So see, this is how it looks. And we're going to use Pelote now. And in particular, we're going to use the edges table to graph function. We need to pass as arguments the data frame that we're going to use. By the way, this also supports other formats like lists, and well, you can check the documentation. I just think that working with data frames is probably the most useful thing. We need to define the source column, so in this case is the station, and the edge target column, so the station from. So this is to define the edges. And you can also, this is optional, but I added the edge data, which is the line. You see, there is line 1 and line 2 of the Madrid subway system. This is only a subset, the subway system is way bigger. And now we can visualize this, for example, with network X. So if I do a quick visualization, see, here we have our metro system. But that's not the end of this quick example I wanted to show you, because now we're going to use Ipysigma, which is the other library. And instead of having a fixed matplotlib like kind of visualization with network X, we can use Ipysigma and import the sigma function and pass the network X object G as argument. And in this case, I'm also gonna pass, this is an optional argument, edge color. The line of the subway, so line 1 and line 2, will be in a different color in our graph. So let's see what this does. Boom. So here we have the two lines represented. Now this looks a bit messy, but if you click here in this play button, start layout, boom, it orders it for you. So it optimizes the visual, and here you have it, line 1 and line 2. You can even select which line you want. So this is pretty neat. There are other things you can do with Ipysigma, but for now, this will be our easy, quick example. So let's now see some more advanced or more complex examples. I'm going to start by creating a social network with network X. This code, by the way, is from the network X episode of Library of the Week, so you can go see how I did this. But basically, the network is a social network, so with people. Each node has a name, an age, and the gender, which are assigned randomly. We use the seed here, so it's random, but it will always be the same. So this is exactly the same network that I created when I did the Network X episode. And we also assign a random weight to the edges of the relationships. The edges are the relationships between the nodes. So now let's see how this network looks with Ipysigma. So here we have this big mess, and I can also order it to optimize it. So here we have males, females. Um, Here the females are green, the males are in pink. And you see we have the nodes, we can select them and so on. So I wanted to work with a different data frame because just like we can create a graph from a pandas data frame, we can also, from a data frame that has been defined with network X or maybe with another network library, we can create a data frame. So in this example, I'm going to use the graph to edges data frame and graph to nodes data frame. Let's do both of them. So in this case, I created two objects, the DS social network nodes. So here I have all the nodes with their attributes. So person 1 is 19, it's a male, person 2 is 41, is a female, and so on. And I also created a data frame with the edges. In this case, we have the source and the target. So this is the key. So person 1 would be related to person 17. So we would have to see if 0 here is related to 17, to 43, to 46, and to 38. And this is what we have here, 17, 43, 46, and 38. So, and we also have the weight, which is a value we assign to the edges. Another very cool function that Pelote comes with is the global threshold sparsification. So let's see what it is. It basically reduces a graph, an existing graph. So for example, in our case, it's our social network. It will remove all the edges that are under a certain threshold. So in our case, our weight has been defined randomly from 1 to 10. It's always integers. And in this case, if I create another G object, another network X object, that I'm going to call social network strong because it will keep the strong relations between the nodes. I apply this function that we import from Pelote, and as arguments I have to pass the original graph, so it's our social network, and the value under which I want the relationships to be removed. And I'm going to use sigma once again, coloring by gender like we did before, to show the result of this operation. So if you noticed earlier, we only had a node, the node number 30. Where is it? It was a female, I think. Yeah, here it is. We only had one node that had no relationships when we created our graph. Now we have three of them, and this is because a lot of relationships have been removed. And you can see that globally, if we go see our graph from earlier, globally we had more relationships before. This has removed all the least strong relationships, and our relationships were defined randomly, so they didn't really mean much. But basically, by removing about half the relationships, because we defined 5, which is the middle value between 1 and 10, and it's randomly assigned. By removing about half our edges, we still have a network where almost everyone is connected. And here we can obviously define other values, like we could remove only the under 2, so we still have a network that looks pretty much like the original one. But if we remove everything under 9, oops, what did I do? here we have something very different. A lot of nodes don't have relationships anymore, and we still have some that are connected, but obviously if we only keep the very strong relationships, a lot of people get disconnected. Okay, as I said earlier, Pelote and Ipysigma are both academic projects, and Pelote as a toolbox also comes with some functions that perform some statistical analysis that, well, you may not need. We're going to see them because it was interesting for me to learn about it. One of them is, I'm not gonna show them all, I'm just gonna show this one, is the multi-scale backbone, and we can define a new network where we apply this multi-scale backbone. So what this does is, let's see with the image, you see this has kept only two relationships, the one between 29 and 24 and the one between 4 and 38. What this does, and I have linked in the Medium article some other scientific articles that explain this methodology. What this does is it will remove all the nodes that are not significant statistically, and I believe that it's not surprising that this function removes almost all the nodes that we created because we create them randomly. So if we apply the backbone disparity filter, we will only keep those relationships that look meaningful according to a certain statistical analysis. This is what this function does. And another related function that is very used to calculate this multi-scale backbone or to generate the resulting graph with the multi-scale backbone function is the edge disparity. So the edge disparity will assign to each edge a score based on the same statistical method that we apply to the relationships. So what I did here is I am applying this function to the social network, and it returns, as you see, for each edge. So an edge is defined as two nodes that are connected. It assigns a value, and our previous function, multi-scale backbone, will only return the edges that are significantly linked. So that will be under 0.05. You can change it. Here, if I wanted, I could have used maybe a very big value, like maybe 0.2. And you see, 0.2, there is a lot of, well, there is more connections. And normally if I put 1, I should have them all, I think. Yes, because here you have to put a decimal value. So usually 0.05, maybe 0.01 if you're looking for very strong relationships. I came here to see, and I printed 24 and 29 because 24 is linked to 29 apparently in a very strong way. So these numbers should be under 0.05, and as you can see, this is 0.02. So we satisfy the condition, and here it is still linked. And now I want to show you a couple of functions that are used to trim graphs. They are the largest connected component and the largest connected component subgraph. So these are basically linked, just like the two before. What they do is they will return a subset of our current graph, which the biggest amount of connected nodes or the biggest amount of edges. So the largest connected component function returns this set, so Python set, and the largest connected component subgraph returns a graph object, a network X object. But they basically do the same operation, just one returns, well, it's not the same operation inside, but one returns it as a set, the other one returns a graph. And if we see it, we will notice that the only thing that has changed, because our graph was basically everyone was connected to everyone except for the node number 30, which you see is missing here because it was alone. So it cannot be in the largest component subgraph. And still, as a subset kind of function, we have the remove and filter leaves functions. So a leaf is a node that is connected to only one other node, like for example 26 or 28 here are leaves. So filter leaves will return another graph. So in this case I'm going to call it social network no leaves. So here we have our graph without the leaves. It is curious to note that node number 30 is here alone again, because this is not a leaf since it's not connected to only one other node. It's basically not connected to anybody, so there it remains. But our graph has now no leaves. So that's it for today. I hope you enjoyed this video. Like it if you liked it, subscribe to the channel and click on the notification bell. It would help me tremendously. And if there is a Python library you would want me to talk about, just leave a message in the comments below and I will get back to you soon. Until next time.